Right, so this project is on optimizing the autopilot for pitch and roll control on an F16 aircraft. And this is a student project, but I'm just talking over because it's got some quite interesting things. So there's some objectives, you can have a look at there, but the main thing I want to get off is that there are some equations which describe the motion of the aircraft, and these break down into longitudinal and lateral dynamics. And in longitudinal dynamics we have the SPO mode and the phugoid mode, and this piece of equipment is mostly associated with the SPO mode, this particular experiment. We've also got lateral dynamics, which I suppose they involve the roll mode as well, so we could use lateral dynamics to get roll mode and the longitudinal to get the pitching mode. And then we've got a closed loop control system which is controlling the pitch and the roll, and they've got inside them PID controllers, and these PID gains need selecting. And one of the things that occurs with an aircraft is as you change airspeed you need different gains, so you need to have different gains for different flight conditions. So it's the same with this. This is in a wind tunnel. As we fly it at different tunnel speeds we will have to have different controller gains, and the system is controlled using a microcontroller called an Arduino, and also that's connected up to the MATLAB program which acts as a real-time monitor and shows you what's going on in the flight control system. You've got different ways of controlling the tunnel speed. I think we'll be using a slightly different wind tunnel, but this is what the F16 looks like in the tunnel here, and it's connected by a little gimbal here, and that can measure the pitch angle and the roll angle. This is a separate plane, but we're just going to concentrate on the F16 for this project. So here it would be sitting in the tunnel, and you could then fly it at different tunnel speeds and control the pitch angle and the roll angle. So then you can do pitch up, pitch down, and roll sort of things. Now this is the sort of things we get out from the results from it. The red line is the desired set point change, same pitch angle. This is the actual pitch angle, and that's what the elevators did. And this might be the roll angle along there. And so we can then do that then choosing different gains and different tunnel speeds, and we can look for the performance. And what we're trying to do is get a nice transient response. This has got a bit too much overshoot here. So nice fast response without too much overshoot. And as I say, these gains have to be chosen, different gains for different tunnel speeds. So this is a slightly better tuned one here, where the overshoot is almost critically damped, isn't it, on that one? This one's got far too much overshoot. And you can also do different sizes of step, so you can pitch it over a bigger number of degrees. This is a 2-degree step, so it's pitching over about 12 degrees up and down. So you can do bigger pitch changes to see how that affects the response. This is a 1.5 and this is a 1-degree step. You can look at the linearity of the system by looking at that. You can also look at the control system behavior, or the surface, how the elevators move and that sort of thing, and the effect on tunnel speed. Sometimes if you design it incorrectly it can go unstable, and it'll start rattling around quite violently in the tunnel, at which point probably you want to switch it off, otherwise something will probably snap off and break. These are some more results here of doing the same. This is increasing the tunnel speed with a fixed gain. So at a fixed, you've designed the controller at a speed of 4.5 meters per second, and then so it's got this performance here, and then we just increase the tunnel speed over time. As the tunnel speed's gone up, the gain of the system goes up, and you can see it becomes less and less stable. Still stable, but it's less and less stable as you. So you can see if you have a fixed gain at the low speed and use it high speed, you'll get into performance problems. So you can't have like one gain that works for across the tunnel. So you could investigate all of these features and then design controllers that will give you a good performance at low speed and a good performance at high speed. This one's designed to be good at high speed, and then as you go down it's become less performance. This is another one where this is using a variable control again, so get reasonable. Still not quite the same everywhere, is it? This is designed in the mid-tunnel point, I think, at about 6.5 meters per second. So you can get loads of results off from your things. I'm not going to go, and I think that's the main thing to see really here, is that you can run the F16 in the wind tunnel, and you can design some control systems for it and look at the transit response, tune up the transit responses at different tunnel conditions, and then make yourself what's called a gain schedule, which is like as the tunnel speed changes, it changes the controller gains to give you a good performance at all flight conditions. And you can do that for pitch, and you can do it for roll. So there's plenty to do. It's quite an interesting project, and it's use the wind tunnels, do a bit of flight control, and that's the thinking behind the project.